Hi, and welcome to Econ 481. These videos were recorded while I taught the class over Zoom, but they were later edited so that the students' faces, their questions, and my answer to those questions do not appear. As a result, the videos are shorter than a normal lecture, and they may have unnatural transitions. But I hope you enjoy them anyway. Bye now. But anyway, let's get started. Let me grab my pen. So this is the fourth lecture of Econ 481, and today we're going to talk about extrapolation and extensions of marginal treatment effects and lakes. And the lecture is going to be based on these two papers that I'm listed here. I, you know, in every lecture, you'll see that I sometimes reference a variety of papers, but the two that I put at the front are the ones that I think you should read if you're interested in this. And these are actually two papers that are quite, I think, interesting to read if you care about these topics. Okay. All right. So this is where we are. We're in this lecture 4 about extrapolations, and so far we cover an entire lecture on selection and observables. We talk about what we could do there. We talk about selection bias, and we introduce the propensity score. Then we talk about selection and unobservables. We introduce the role of heterogeneity and observed heterogeneity, and then we describe the Roy model and the local average treatment effect, as well as ways to incorporate, for example, covariates through stuff like the Avadis kappa. Then we talk about the marginal treatment effect, all the work by Heckman and Bidlasil, and we define, we show that we can write a lot of parameters we care about as functions of the so-called marginal treatment effects, and then we introduce the policy-relevant treatment effects, which are parameters that you can describe clearly in the context of MTEs, but that are like much harder to describe in general. In other contexts, may not even be well defined. Okay, and so we also discuss about the relevance for policy of parameters like this versus standard parameters like the average treatment effect, for example. So today we're going to continue with this philosophy, but we're going to try to see if we can say something more. And then we're going to try to combine everything that we learn into some approach that will essentially use all the pieces that we learn and put them together to start asking questions about parameters that we defined before. Um, you know, we ask ourselves, what is that we can do? Okay. So it's more about what do we want to do, and then let's see if we can do it, as opposed to, okay, what is it that we can do, and let's see if that's interesting. Okay. So that's what we're gonna do today. In terms of the outline, I'm gonna be talking about parameterizing MTEs, which is the first paper that I listed before. They have an application of quantity quality infertility, QQ infertility. We're gonna go over that briefly, and then we're gonna present the paper on extrapolation by Mokstad, Santos, and Torgovitsky. They have an application to BetNets, which illustrates that things are feasible, because one thing that will happen with this paper is that when you look at the theory, you may wonder or have concerns about whether things are really feasible or not, or computationally tractable, if you want. So the application will help us get a sense of whether that's the case or not. All right, summary. Unobserved heterogeneity, widely viewed as prevalent and important in applied work. I think that so far we should convince ourselves that that's the case. There's the fully parametric selection model that we described. It was the Heckman two-step estimator, but it has the problem of being parametric. And in 2020, we think that we can do better than that. There's also the linear IB models, okay, with heterogeneity, is the stuff that led to the late, okay. But we know that in general, when we start having covariates and perhaps multiple values of the instruments and so on, at best it gives us some sort of weighted average of lates of some form, and it is unclear sometimes what type of policy question parameters like that would be answering. And then we had the marginal treatment effect, which gave us a framework to define a variety of parameters, including the ones that we knew already and the new ones that we define as policy relevant treatment effects. But one thing we learned is that in order to identify something like the marginal treatment effect, we needed to have a lot from the instrument. In particular, remember, we need to have a continuous instrument with a propensity score that will have large support. And then we had all these issues that these conditions became more stringent as we had covariates, because then we needed the propensity score like to have these conditions for a given value of the covariates and so on. So um but this is sort of like a picture of what we have. And the next thing that we're going to be talking about today is extrapolation. I wrote here, we want to extrapolate from those affected by the instrument to others. Think about the late, okay? Those will be relevant in our counterfactual question. Later, we're going to talk about this QQ infertility application, where again we're going to be using this instrument, which is whether the families got the first two kids of the same sex or not, and we're going to be using that as an instrument with, again, this assumption that people have preferences for having kids of both genders. And one thing about that is that we can estimate or identify a parameter like the late, which are these individuals that are affected by the instrument. And the question is, can we say something about other type of individuals? These are defined as the compliers. What about the always takers? What about the never takers? And can we learn something about the compliers and then say something about the others? And then that is called extrapolation. Of course, we will require to make some assumptions, but we'll see. So, natural way to do this to add some attractive, I wrote here parametric structure, okay? Some fully parametric model. And in this case, for example, would be the normal selection model that we saw that allows you to answer all these questions and extrapolate sort of like everywhere. But the problem is that, these models, have a lot of structure. And in principle, we would like to avoid that. And so if you are not willing to add a lot of structure, then, by now and by the courses that you've taken in this 480 sequence, you know that an alternative way to proceed is to start thinking about partial identification. And then you say like, okay, perhaps I will not be able to point identify all the parameter of interest, but I may be able to place bounds on them or find identify sets for them. And then, I will be able to extrapolate under more credible assumptions, but at the cost of having less precise predictions of what will happen for those that are not directly affected. Okay. And this is sort of like where we are and where we're going. So I wrote here the easy way out. Again, it's just today I'm going to say a lot of things. So I want to kind of like start easy. But by the end of the lecture, we're going to be covering a lot of stuff. So the easy way out, I wrote here, is to understand that all identification issues are caused by unobserved heterogeneity, right? The U, the selection equation, is dependent of the potential outcomes given X, and in particular, dependent about the difference between Y1 and Y0, which is the treatment effect for individuals, right? If we assume that there is no such heterogeneity, right? So you can say expected value of Y1 minus Y0 condition U and X is just the expected value of Y1 minus Y0 condition on X for all U. Then this is, assuming that the marginal treatment effect is constant as a function of U. Okay. And so any condition on X late is sufficient to point identify an entire marginal treatment effect, because you will identify the marginal treatment effect in some area and then it's constant. So you can just extrapolate here and there. So a condition like this will happen, for example, if we have constant treatment effects, okay? Meaning Y1 minus Y0 condition on X is deterministic, okay? And, as I wrote here, it will hold more generally when agents choose D with no knowledge of their potential outcomes, okay? This is sort of like cheating in a way, but you could say, oh, look, my assumption here still allows for selection, okay? Because I'm not assuming that the expected value of YD condition U and X is equal to the expected value of YD condition on X, okay? I'm assuming that the difference okay, that it get difference out. So I wrote here, it allows for selection bias, okay, but it doesn't allow for selection on the gain. However, it's, as I said, it's kind of like cheating because you have to have a story perhaps to say why something like this would happen, okay? But in principle, is a story that is kind of like not so easy to tell. In terms of a simple case that will give you something like this, imagine if you just model potential outcomes like this, y1 equals like prime beta 1 plus u, and y0 equals x prime beta 0 plus u, where on purpose I just wrote the same u on both equations, right? It's not u1 and u0, right? And then if you just compute the difference of y1 minus y0, you'll see that it is x prime beta 1 minus beta 0. And that's it. So conditional on x, that's going to be deterministic, right? Still different. There's heterogeneity, but the heterogeneity is, as we said, observed heterogeneity. And, but this is a feature of just adding the same u on both equations. Important to pay attention to these details if you are ever working on something related, and then people do simulations and then they simplify things. Make sure that you pay attention to these things because you may be simulating a model that is imposing a lot of structure just by the fact that you're just using the same, say, error on both potential outcomes. Okay. The minute that you have u1 here and u0, then automatically you're going to have a term that is going to be u1 minus u0, and this is now no longer going to hold. So the summary is most endogeneity stories feature both forms of selection, okay? Selection bias and selection on the game, because you will believe that the true model is something that looks like that, at least. So for this paper, the first paper by Brinch, Moxton, and Wiswall propose is to parameterize the marginal treatment effect. Okay, and so I'm gonna abstain for now on the axis. The paper has a lot of axes, and as I said, I think these are good reads. So if you care about these topics, I would highly recommend that you read both of the papers that we're talking about today. But if you read the papers, you'll see that they, of course, include the axis from the get-go. I'm going to abstract away from the axis to keep my notation simple, okay? And then I'm going to bring them back to explain what are the consequences, okay? So without covariates, we're going to define this MD over here that sometimes is called, and we're going to call it this later, a marginal treatment response, which is just the expected value of the potential outcome conditional on the unobserved heterogeneity. That's an object that appears in the marginal treatment effect because it's just the difference of M1 minus M0, difference between these two marginal treatment responses. So what this paper is going to propose is to say, okay, we're going to parameterize this as a function of u. And here I'm going to say, for simplicity, let's start with the case where this guy over here is linear. So you're assuming that the marginal treatment effect is a linear function of u. And so we just put it together, and then the marginal treatment effect is also a linear function of the unobserved heterogeneity. And so when you compute the expected value of the observed y, condition D, and the propensity score, and D1 and D0, then you have these two equations, okay? And so if you regress y on P and D to identify, you can identify beta 1 and alpha 1 from this equation, and sorry, beta 0 and alpha 0 from this equation, okay? And this even holds if you have an instrument with 2 points of support. So notice I wrote here implication, hopefully you're paying attention, that we learned before that in order to identify the marginal treatment effect, we needed an instrument that was continuous and then a propensity score that had full support, okay? And now by assuming that this marginal treatment effect is linear, we can identify the entire marginal treatment effect function with a binary instrument, okay? Of course, we're imposing an assumption, but then you see that this is not assuming that there is no unobserved heterogeneity here. The marginal treatment effect function actually depends on U, is not flat in U, which would be no heterogeneity. So it is allowing for heterogeneity, it's just allowing for a specific type. Also note that, as again, it will be important later to know that if you just, that this identification argument that I just provided, it is exploiting that you're running sort of like two regressions separately. One's for the one and another one for the equal to 0, as opposed to just a regression of y on the and p. Okay, which would be will not be enough, or y on p should say. Okay, sorry. So okay, that was linearity. And then you may say, like, well, assuming that the marginal treatment response linear is sort of like strong, okay, then we can think about being more flexible and allowing this function to be a polynomial. So in this case, what will happen is that when we compute the expected value of y conditional on d equals 1 and p equal to p, this will be a kth degree polynomial in this case, where again, you see here that the polynomial that I'm imposing in the marginal treatment response is k. And so what happens in this case? Well, you can show that we can point identify the polynomial of degree k, okay, as long as k is equal to the support of the instrument that we have -1. You can rephrase this. We need the support of our instrument to be at least equal to k plus 1. If we just think about the previous example, in the previous example, k was 1, okay, because it was linear. So k plus 1 was 2. And then we needed an instrument with 2 points of support, binary, okay? But if you're now having a 5-degree polynomial, you need an instrument with at least 6 points of support to point identify all these coefficients in the polynomial. And again, as I said yesterday, stratifying on D is important, okay? And this is again discussed clearly, and there's an entire page of discussions on this in the first paper that I'm listing. Because otherwise, if you just compute the expected value of y conditional on the propensity score, as I said before, you have this equation over here. Now it is quadratic in the linear case, okay? So notice that in the linear case, you have this. And so you want to identify all these parameters. And in this case, you need a trinary instrument. So identifying the parameters really matters how you, quote unquote, run these regressions. And how you run these regressions may affect the requirements that you have on the instruments. And so stratifying on D gives you identification with a binary instrument. You don't stratify on D and you were just to use an equation like this, you will need an instrument that takes 3 values at least. Okay? So we're removing 1 point in the support by stratifying. Which again, you say is 1, but then since quite often the instruments take few values, this is a relevant restriction. So, as I said, that's sort of like the intuition without the covariates. Then later on, of course, you're gonna want to introduce covariates. And so when you look at the marginal treatment response here, I'm gonna start with an easy case, the case where x is just binary, okay? And so you look at the marginal treatment response of the first potential outcome, and then you write it as a constant, component that depends on x, component that depends on u, and the cross product. So this you will call like fully saturated. Then you compute the expected value of y given d equals 1, p, and x. And then you have this equation over here, which includes now x, the propensity score, and the interaction term. Okay? So now what we need is an instrument requirement conditional on x. Okay? And we need variation in the propensity score given x equal to 0 and x equal to 1 to identify alpha 1 and beta 1 and gamma 1 and delta 1, which are these parameters over here. So in general, whenever we have this type of interaction terms that appear here and here, the requirements that we're going to need on the instruments are going to be quite stringent because everything is sort of like have to be conditional on x. Okay? And so, as we saw in the class that we described marginal treatment effects last time, One way to deal with this that, gives us identification where we can just use the unconditional variability of the propensity score is by imposing separability. So that is, in this case, removing the interaction terms, and that is removing delta 1 from the marginal treatment response. And so, it's just a constant, a component that depends on X and a component that depends on U. And now you compute the conditional expectation as before, and then you see that you have conditional expectation that is separable in the X's and in the propensity score. Not only has fewer parameters now, but as I said, in general, it will allow us to use variation in the propensity score that is unconditional as opposed to conditional on X. So then, if you just look at what the vast majority of the papers using marginal treatment effects, to my knowledge, is that at some point, sometime explicitly, like in this paper that we're discussing, another time is kind of like implicit, so you have to pay attention. They're going to impose separability. Okay, so this is a very common assumption. Just we saw the application last time that condition on X, the propensity score essentially had very limited variability. So you would have been able to identify the marginal treatment effect function only in very specific. So in a way, there's no way out here. It's just a trade-off between how flexible the model can be and what's the identification that you get out of the model. All right. Questions about that? Okay. Well, whatever. Let's move to the application on QQ and fertility. So QQ stands for quantity, quality, and fertility. This is the application of this paper that I'm talking about. And so let's start from the beginning. So I said we're going to talk about this application in this paper that we're talking about. And the thing is that this is one of these applications in which you want to say, in this case, you want to know the effect of family size on the child outcomes, actually the outcome of the older children. And so, you can tell a story in which this effect could be negative. I wrote here because of resource dilution. It's like you're a parent, now you have 10 kids and then you cannot devote that much time to your oldest one. But it could be positive because, here I wrote marriage stability, which I'm not sure. Also finding the other way around, but you can say that also there's support from siblings and other things. So, anyway, the thing is that this is clearly one of those cases in which you can find effects on one way or the other. And the data here that they are going to use has been used in other papers. For example, this one by Black, Derbo, and Salvanes. And it has a lot of data from Norway. Y is the firstborn child's years of attained education. That's our outcome. The treatment and instruments are the same that we describe when we talk about in the paper of Angris and Evans. Okay. And D is an indicator of having more than 2 children versus exactly 2. Okay. Remember, the Z is either twins or same sex. We're going to be using the same sex mostly. And X includes covariates in general that are the usual suspects. All right. So here, the first table is just report a bunch of IB estimators using different instruments, the propensity score, just the instruments, and, the instruments that we're talking about, or both. Okay. Is there something that I want to highlight here? I think that the main point that one can take from these things is that, if the instruments are valid, okay, and the effects are constants, then you would expect these estimates to be roughly the same, right? Because remember, different instruments are in this world are identifying different local average treatment effects, okay? But if there's not an observed heterogeneity, these local average treatment effects are the same. And if they start looking different, then you have some indication that there's unobserved heterogeneity. Of course, another problem could be that the instrument is not working, but as long as it's introducing some variation, if you see different values here, you have some indication that you have unobserved heterogeneity. So now this table is interesting because what they do is this estimate the linear marginal treatment effects that we described before as linear. When you're linear, you essentially have to find these four parameters that in my notes I call like alpha 1, beta 1, alpha 0, beta 0. Okay, in the paper they have all this different notation, but essentially you can see that you have a binary instrument here because it's the same sex. Okay, and then you have two values of the propensity score, and they essentially estimate these low parameters. And one thing that is discussed in the paper that I'm not going to devote a lot of time, but is that when the marginal treatment effect is linear, and then you assume a linear marginal, well, and you make that assumption, then you can estimate the late by using the formulas that we learn um, using the marginal treatment effects by integrating the marginal treatment effect over the relevant range. Okay, in this case, notice that these are the values of the propensity score that we have over here. Okay, or you can just do it by an IV estimate or a wall estimate. Okay, well, not surprising here, these two things are exactly numerically the same because in the paper you can see how when you assume a linear marginal treatment effect, you can show that the representation of the local average treatment of the late like this coincides with the IV that you have over here. So it's exactly the same. So I wrote here, there are no covariates in these specifications, okay? And that's why you have, in cases like this, really large standard errors. The linear MT model replicates the late, okay? Well, that was in some problem set, not now. Linearity means that the MTE is point identified everywhere, okay? And this is something we discussed. You have two value points of support. Now you identify the entire function everywhere. Whether this is credible or not, we're going to discuss it in a minute. And then provides an average treatment effect of 0.02, which I forgot what it is over here. Perhaps it's not here. And an average treatment on the treated of 0.48, which, we don't have much to say um, about those now. So look at this. These are the estimate of a non-parametric marginal treatment effect function with separability imposed. Okay, this is sort of like along the lines of the work of Canay, Heckman, and Bill Lasil that we discussed last class. And you look at the marginal treatment effect function, and doesn't look constant to start. So if there was no unobserved heterogeneity, you will have a flat line. Okay, so then you can say that. The other thing, it doesn't appear to be linear. Okay, so the previous table where we estimated the marginal treatment effect assuming linearity doesn't seem to fit well with this representation that we obtained here from the non-parametric T. But more importantly, if you just grab 0 here just to make it simple, and let's pretend that was a straight line, you can essentially find 2 points over here and here, let's say, more or less. And then remember, this P here is our, you can say our U, right? And so what you say is that people that have low values of U's, okay, have a positive MTE. And remember, low U is D equal to 1 often. Okay, because remember that D is the indicator that U is less than or equal than P, right? So a low value of U means that this type of individuals over here choose D quite often. So in other words, they're not really much affected by the instrument. Okay, these are people that always decide to have more children, regardless of whether the first two were the same sex, different sex, or whatever. Okay. Whereas if you just look at high values of U over here, this is always also have a positive MTE, and this is high values of U. High U is the 0 often. So these individuals over here are individuals that typically don't have a third child. Okay, regardless again of whether the first one was um, a twin, or sorry, they had the same sex or not. And then you grab the people in the middle that are roughly those that are affected by the instrument. Okay. And it happens to be that those individuals have a negative marginal treatment effect. So the response is heterogeneous. And also, funny thing is that, for those that you will be able sort of to identify with something like a local average treatment effect, those are the ones that are negatively affected, okay, by this. Whereas, you can see that there are other type of individuals in this case that will be positively affected. So, which illustrates also that extrapolating is not so straightforward, right? Because one, of course, a simpler way to extrapolate is like, well, if I find a negative effect for compliers, I'm going to assume that other groups also have negative effects, which clearly is not the case. So, so from here we learned that the marginal treatment effect that is not constant, doesn't seem to be monotonic, and that there are like um significant, or there's at least graphically suggestion that there is an observed heterogeneity. And actually, what they do here in one of the tables is comparing the weights across different intervals of the propensity score, which is again one of the tests that we saw last time to see if there's heterogeneity, and the p-value in this case is 0. Okay, so here the evidence is a lot stronger than in the paper by Carnero, Hickman, and Bitlasil. Okay, suggesting that you you have heterogeneity present in this model. Actually, as we can see, the sign, even changes despite being sometimes significantly different from 0 now, which is irrelevant. Okay. So, that's that about this paper. Okay. So the point of this paper, like if you just want to learn in 2 words, whether it's unfair to the paper or not, is that sometimes estimated marginal treatment effects non-parametrically could be problematic, even if you assume separability, and that assuming certain structure of the marginal treatment effect as a function of the n observables may give you an easier model to deal with, while still allowing for cases like this one over here, right? Which, for example, a quadratic model capture reasonably well. Okay. Questions? All right, Mokstad, Santos, and Torgovitsky. So the idea is that, first of all, I wrote here, we want to specify precise parameters that answer specific questions. Okay. The MT framework provides a good way to do this, but shows these parameters are often not non-parametrically identified. So there are 3 options when you are in a case like this. You include more assumptions, you think about partial identification, or you change the questions. All of this we've seen in different versions. Okay. Sometimes people will refer to something like this as moving the goalpost. Okay. Which happens. Like you just wanted to ask a question about something, you cannot say anything about that. Well, you say something about something else. Or you just start adding assumptions until you get what you need. For example, we saw that with the linear marginal treatment effect in the previous slide. And then what we're going to do now is to try to have a compromise and do things in order. First, we specify the question. Then we include the assumptions that we think are, let's call them, reasonable. And then we are going to follow an approach that most often will lead to partial identification. So I wrote here motivation relative to the previous paper. More assumptions, but functional forms dictated by instrument support. This reflects a framework that requires point identification. Remember that we learned that the support of Z needed to be greater than or equal than K plus 1, where K was the degree of the polynomial. So in a way, this is a setting, since we're thinking about partial identification, that is telling us what we need to identify a given polynomial. And then, think about the previous example that we saw in the previous paper. The instrument there was binary, right? And so, yeah, you say like, oh, but the marginal treatment effect look quadratic, whatever. Let's just do something better. while still, you know, sometimes you will have the situation in which you will want to estimate, say, a polynomial, but your instrument is just going to be binary, and so you're not going to satisfy this condition over here. Just that's what you got. So here instead, we would like to take the assumptions as the primitives. First, we're going to impose the assumptions where we're going to say we're going to estimate a polynomial of degree 5. We're going to assume that the marginal treatment effect is separable, or whatever it is, assumptions that we're going to impose. And those are going to come first before we look at, say, whether our instrument is good, okay, or bad. And then the idea is that if we follow this approach, we can still make informative statements, even if we are not working under a framework that requires point identification. Okay, so I wrote here, we also like to treat the parameter of interest as central instead of deriving it from marginal treatment effects as a second step. So, and if you look at the paper, they have these labels for the sections that I think are quite clear about how they want the reader to think about it. So, if section, say, 2 after the introduction would be called what we want, section 3 will be called what we know, and section 4 will be from what we know to what we want. So the paper is structured in this way that they want you to think about it in this way. First, tell me what you want. Then you tell me what you know. And then I'll tell you how we can go from what you know to what you want. Okay? And again, of course, they're always, the paper is trying to be very clear about, or trying to separate from the way that a late follower would think, right? Which is just, I'll tell you what I know, which is late. And then, you'll tell me what we can do with that. Just as I said at some point, reverse engineering, which it doesn't mean that late is not useful, because it is. It's just conceptually different way to think about it. All right. We're going to assume that the analyst has a target parameter. I saw before I wrote what we want. Well, what we want in this notation is going to, it's going to be beta star. We're going to be later to say what beta star is, but think about any type of parameter that tries to capture some policy question that you care about. In principle, you can think about broadly as a policy relevant treatment effect. So here, beta is defined ex ante, okay, as a parameter of interest, and the only requirement that we're going to put in beta star is that it takes a particular functional form that we're going to describe in a minute. And in particular, we're going to require, which is going to be the case as we know for many parameters, that beta star is a function of the marginal treatment responses, M0 and M1, where MD is the expected value of YD conditional on U. Okay, this is what we just called before the marginal treatment response function. I wrote here, there are two constraints on the marginal treatment response functions. The first one is that they must be observational equivalent, so it might be consistent with the data. We're going to be clear about what that means in a second, okay? But in a way, like if the data is given at certain moments, whatever marginal treatment response functions we have, they have to be consistent with these moments that we find. And then the second one is must satisfy the assumptions that we impose. So for example, if we're going to assume that the model is separable, well, of course, they need to be separable. If we're going to assume that they're monotonic, then they need to be monotonic. So we're going to impose assumptions on this marginal treatment response, which could be one way is no assumptions aside from, say, separability, or no assumptions at all. But we're going to define, okay, this set here that I'm calling script M as the set of assumptions that we're going to impose on the function. Okay? And then when you put both together, they're going to lead to a feasible set of functions that we're going to call script M star. So what are the possible values of beta star? Well, they're going to be all the beta stars such that M belongs to these um, M star. So you can write it here. I don't know if it's in the next slide, but let's write it here. So B star here will be all the beta stars M, or an M that belongs to the script M broadly. So suppose now beta star, suppose beta star M is a single number for each pair. Okay, so here is a scalar. It could be a vector, but again, we're gonna work with this case. So that means that this set B star that I wrote before is just gonna be a subset of the real line, hopefully. And so what we're gonna assume in this paper is that beta star of M, which is again M0 and M1, can be written in this way. It's a sum, from the two treatment states, the 0 and the 1, of the expected value of the integral of the marginal treatment response, weights, and the U. And the expectation here, of course, with respect to X and Z. And so going back to the question that you just asked before, then we know the functional form, okay, as a function of this marginal treatment response. And when I say that, I mean that we know these weights over here, okay? Here it says identify weights. And by that, we mean that we know the functional form and we can identify these weights from data. The weights, as I wrote here, can usually be derived from the choice of parameter that we care about. Covers basically any mean contrast, okay? ATE, ATT, late, policy relevant treatment effect, etc. It's not covering things that are not linear in these functions, okay? Hickman and Bielasil and MST is Moxta, Santos, and Torgovitsky provide a lot of tables that will give you this type of parameters for different target parameters that you may care about. And in many cases, not all, but in most of them, you have that W0 is just negative W1. So these weights are symmetric. You can see this, for example, in the following table. Here you have for some parameters, average untreated outcome, average treated outcome, average treatment effect, ATE conditional on some X, the ATT, ATU, late. Okay. What's the expression of the parameter? This, you all know this. Here you have the weights W0 and W1. And as you can see, there are a lot of cases in which the weight are just the negative of the other one. Okay. So, and then you see, if you just look at the functional form, just indicator X is equal to little x divided by the probability X equal to little x. You have the indicator that U is less than or equal than the propensity score. U greater than the propensity score, U in between these two values of the propensity score. And remember, then the expression we're integrating over U. So we're integrating over those numbers, okay? Because we have this integral over here. But clearly, you know these weights. We know these functional forms. The only objects that we don't know are the marginal treatment responses. While here there are more cases. I'm going to take this opportunity to answer one of the questions that I got earlier today, which was something along the lines that policy relevant treatment effects are similar to intention to treat. And I responded that that's not the case, but it's true that before we didn't give a lot of examples of policy relevant parameters. So we sort of like describe them generally like this, okay? But look at here. One policy relevant treatment effect that we can think about is increasing, okay, the propensity score by an order of magnitude alpha, okay? Now you make the propensity score higher for the same, keeping the values of x's and the instrument constant. And then in that case, you have that this are the weights. You're going to have a plus alpha over there. You can do the same by, making them larger proportionally. The new propensity score you care about is just some magnitude above the previous one. Okay. You can also like change one of the components I wrote here. Policy relevant for an additive alpha shift on the jth component of Z, like assuming that you have more instruments. So in that case, the new propensity score stays the same as the old one. All this you can see that are not related to the intention to treat. Okay, which the intention to treat will just be expected value of y1 minus y0 conditional on the instrument being equal to say 1. Okay, that's what you gave. Care about whether the individuals actually you gave them the medicine. You don't care so much about whether they took the medicine or not. Whereas here you can ask a wider variety of questions that two that you're gonna see sometimes are like shifting the propensity score additively or multiplicatively um, to explore this type of policies. Okay, so what do we mean by observational equivalence? So now moments of the distribution of y, d, x, and z are similar to the parameter of interest or the target parameters, meaning that we can write them as functions of the marginal treatment responses. So we're going to let s be a function of d, x, and z. So s is just a function of this. And we're going to define something called the IV-like estimate. It's going to be beta s, effective value of y times s. Okay. So the idea here is that if you just look at, for example, IV, essentially squares and these things, that they typically take this form. Okay. Think about least squares, x prime x inverse x prime y. So then you're going to have that all these first things, functions of x are just going to be s in this notation. All right. So this is the part in the paper that if you take a look, which is in the paper, is called what we know. Meaning you can grab your data and you can do least squares. You can grab your data and you can do IB. You can always do these things. These are just moments of the data. What's true is that often the least squares or the IB will not tell you the value of beta star. Okay. But they will tell you something. And so in this paper, what we're going to try to ask is like, okay, what if we know these moments and we just go from these moments to the parameters that we care about? And that's the part that we're going to discuss here under observational equivalence. So the mapping between the marginal treatment responses and beta S, which are these IV like estimates, is just going to be defined by this gamma SM. Okay. And again, if you just look, it takes the same form that we described before, except that now these weights, okay, are just going to take this particular form where, you have an S function multiplying an indicator of U being above or below a propensity score. Okay, so I wrote here same structure as the target parameter beta star, but different weights. And I'm not gonna write this in a supplement. I don't know why this is here. Perhaps should have removed this, but you can look in the paper where these things are derived. Here, there's a table where you can see, for example, some standard cases. The wall estimate, okay, which is this guy that we've been using so far. Well, S in that case is just this function over here. Okay, if you the IB slope, the S is this function over here. The IB for just one component is just this one. And you can keep going with two-stage least squares, OLS slope, OLS of the J component. You see the derivation of all these as functions that gives you the weights. And so now you can see how this is going to work out, because we're going to be able to know some of these guys. For example, least squares and IB. And we know that these parameters take this particular functional form where we know the weights, we know the functional form. What we don't know is the marginal treatment response. But not any marginal treatment response will typically be consistent with a given value of the IB. So for example, suppose that we have beta IB is equal to 0.68. Okay. All right. So then it has to be that any two functions that you give me, M0 and M1, are such that when you compute this integral over here, you get 0.68 in return. Okay. And if you just give me two values that do not give me 0.68, well, those are not observational equivalent. Observational equivalence means any two values of this vector M0 and M1, it means values of the marginal tumor responses that deliver the same value of the things that you know, which in this case, I'm just saying, say the IV. Okay. So hopefully this is going to restrict the set of marginal treatment responses. And then this is going to lead to a restriction on the set of betas that the target parameters that we care about. So imagine this is like what I call like B star, okay? And this is what I call M star. We know that there's a mapping from here to here, right? But then now we're saying, well, I know that I have an IB like estimand. So all the values of the marginal treatment responses, okay, these are the observationally equivalent, say, with IB, okay? These are all the values of the M1, M0s that are consistent with the value of the IB that we have in our data. So now what we have is that this maps into some set here. And, you know, this is just going to be values of our target parameter that are going to be consistent with our assumptions and consistent with what we know, which in this case are this like IB like estimate. Despite not being a beautiful picture, this illustration is sort of like exactly what's going on. Now we're gonna describe this mathematically, but just wanted a graphical illustration. That's what it is. So identification. We're gonna find bounds through optimization. The idea is this. Suppose that we pick some class of estimators to get IB-like estimates. Here, just make it simple. Suppose that S only includes two, IB and OLS, two. Okay. Then we're going to construct an upper bound or lower bound for our parameter of interest or target parameter by computing the supremum over the functions m's of beta star m, such that these functions satisfy our assumptions, and these functions gives us the value of the IB-like estimates that we are considering. In this case, IB and least squares. Okay, so suppose IB is 68, least squares is a half. It has to be that when you plug into these formulas that we know, you get 68 and a half. Okay, and then instead of taking the supremum, we take the infimum, and then we get a lower bound for the target parameter. And then at the end of the day, what we have is that this is going to be an outer set of the identified set for the target parameter. Okay, but this is what we're going to use. The advantage of this, as we're going to see in a minute, that is this guy is linear in M. This guy is linear in M. Okay, and so if we impose assumptions so that they can be expressed as linear functions somehow, then we're going to have a linear problem. However, this immediately is not obvious because M here are functions, okay? That so far, they're kind of unrestricted. All right? So how do we do this in practice? Can these problems be made feasible? Turns out the answer is yes, if M has a particular structure, which is sort of like what I hinted already. And are these the best bounds possible for a parameter like this? Well, that would depend on what are the IB-like estimates that we're considering. Are the bounds useful? It depends on the target parameter. the assumptions that we're imposing and the data, but it's going to be clear in a minute how this play a role. And then we will have this type of monotonicity where, one you already know, which is the more assumptions you impose, more structure you impose in M, the narrower our bounds are going to be. But here we're also going to have this feature that the more features or IV like estimates we include, the narrower um, um, the bounds are going to be. And if you think about it, it's not surprising or should not be surprising because this is one way of saying what we know. What we know are the IB parameters. And the assumptions is another way of saying what we know because it's what we're assuming that we know at least, okay, which are the assumptions imposing in. So both beta star and the gamma s's are linear functions of M. We saw that. We have the expressions. If this script M is a polyhedral, the optimization problem, as I said, are linear problems, okay? They're finite linear problems, can be solved quickly and reliable. There are a lot of research and software for doing that, okay? The problem, as I said earlier, is that M is a function, okay? And so what are we going to do? Well, we're going to parameterize this function in a way that we believe it is flexible. One way of doing that is using, for example, linear basis. Okay, so in this case, just going to write MDUX as something like this, where this B's here are known bases, and now the thetas here are going to be the unknown parameters. So now when we write beta star M0, M1, it's just the parameter is theta, and then this is linear in theta, is finite dimensional and linear. So now we can write this as a linear program. Okay? This is one way of doing it, but there are other ways. For example, you can use Bernstein polynomials, and that, well, I mean, this is the way. The question is now, what are these known basis functions that we have? One of those would be Bernstein polynomials, okay, and another one would be splines. The advantage of these two basis functions is that oftentimes we will want to impose some assumptions, okay, on M. For example, we want to guarantee that the functions are bounded, monotonic, concave, okay. And in both of these cases, this type of restrictions can be imposed by just linear constraints on theta. So as long as we have a linear program, has linear objective functions and linear constraints, then we're going to be able to exploit the machinery of solving linear problems. And then this is what they're going to propose and do in these papers. So here are three assumptions that are routinely imposed. These are not the only ones that you may want to impose, but these are easy. First, in general, as you may know, you may have seen this with Chuck, and whenever you start talking about expected values of random variables, you need to assume that these outcomes are bounded, because otherwise the expectation may be unbounded above or unbounded below, right? And so, in some cases it's obvious. For example, if y is binary, you know that it is just between 0 and 1. In other cases, you may have a natural lower bound. You're talking about income, and you're going to assume the income is bounded by 0. Same with the education and other things. Sometimes there's a natural lower bound and a natural upper bound, but in other cases, you will need to impose some upper bound as well. Okay. So for the polynomials and the splines, these are constraints on the values of these thetas. So it's very easy to impose boundedness on the outcome. Monotonicity also can be imposed by inequality constraints on the theta in both of these cases. Okay. For example, you can assume that the marginal treatment response are decreasing in U, or you can assume that the selection of the gain is positive or negative, or both. Okay. And then finally, one that is going to be particularly important, as we described before, is separability, right? We sometimes want that the marginal treatment response and the marginal treatment effect are separable in the U's and the X, because again, this is what allows us to get identification by the unconditional support of the propensity score. And so the way to do that is by just using these basis functions that are separable, or in other words, impose that the cross terms are 0 for interactions. And that's essentially it. So here you have then boundedness, monotonicity, separability. They're easy to impose. But as I said, if you wanted to impose things like concavity or other type of shape restrictions, it's not difficult to do with those two families of basis functions. Next question is choosing IV-like estimates. Okay, the bounds necessarily get smaller the more stuff you put in what we know. The paper shows that the smallest bounds are achieved by making S rich enough. So when you're thinking about identification, if you ask me, do we need to add more? The answer is, of course, just add everything you know. Okay. So for identification, the only drawback is increasing S is computational, but just keep adding. The problem is that when it comes to statistical inference, the more stuff you add may complicate inference. And so this is still something that is not fully worked out. If you care about inference, there are two versions of this paper. One is the version that got published in Econometrics, and they asked them to remove inference from the paper, so it doesn't have any inference. But if you just look at the NBR working paper version, that version had an inference approach, and the reason why somebody like Andres Santos is in the paper, which is to bring that to the table. So, but the published version, they didn't want the paper to be that long, and it doesn't have inference. Still, inference still tricky in linear programs in general, and is an area of research right now. Some people are working on that. It's not a trivial part. We're not going to talk much about it, but here you have of course a trade-off that is not so easy then to say just go and add or make S as big as you want, because you may have difficulties when it comes to inference later. Any S I wrote here, including S, must be consistent with the derived bounds. Okay, so for example, suppose that you just include one late parameter, so the bounds are going to be able to reproduce the late. So what's good is that you will have a model that will identify a marginal Truman effect. And if you use, for example, your late or your IB estimate as part of your bag, as part of your S over here, your model is going to deliver when you ask the question, okay, what is the effect from moving from here to here? Just going to give you the late because it's going to be consistent with that. Okay, and that's the form we can say of internal validity. Like you're just going to be able to replicate exactly the same effect that a person that doesn't care about all this will get. Okay, as long as you include that in your bag of S, of course, right? If you don't, then that's not going to happen necessarily. But then, of course, the approach is going to allow us to do extrapolation because, as we said, some of these questions that we're going to ask are not going to be directly estimable. They're not going to be even point identifying. They're the assumptions that we're discussing. So hopefully, the idea is that we're going to get the best of both worlds. And what I wrote here is a natural approach might be to include common estimates in S with this like doesn't hurt to look kind of attitude. Okay, so you want to include IB, you want to include least squares, just put them there. And if there's something else you say like, well, maybe I can include this other thing, well, you can just put it there, and then you recompute and see what you get. Again, since we're not talking about inference, and this is a paper mostly about identification and estimation, all that is fine. So let me show you an illustration of this that is taken from a previous version of the paper, actually. This is motivated by the empirical application that we're going to see later. D is 0, 1. It's going to be the purchase of a bet net. And then Z is going to be 1, 2, 3, 4, which are going to be randomly assigned price subsidies that happen in this experiment. Okay, so the marginal distribution of the instrument is 1/4. So you're assuming that you're assigning these treatments with equal probability. And the propensity score are like, 0.12, 0.23, 0.48, okay, 0.78. Okay, so this is probably you purchase the bet net. And so this is low, this is high, this is a generous discount or subsidy. This is at least generous discount of subsidy. Okay. So we're going to suppose that Y is just binary, is whether you get infected with malaria or not. And D is endogenous, if individuals know their propensity to contract malaria. For example, if they live in an area with a lot of mosquitoes, what's their house, and so on. Other information they may have. So the first picture over here is in this setting. There's a plot of the marginal treatment responses and the marginal treatment effect. So here you have M0, here you have M1, and here you have M1 minus M0. All of these are non-constant, so it means that we have selection bias and selection on the gain, as we discussed before. I wrote here, those less likely to buy a net are more likely to get malaria anyway in this example, because here is the U, right? So those more likely to buy the bet net are more likely to gain from it. Okay, so you have these two different forms of selection. As we said, selection bias and selection on the gain. What's more interesting is this. Here you have bounce on the average treatment on the treated. Okay, and then what we're doing here is considering different degrees of polynomials, and we're also having some non-parametric using these splines and so on. And so what we see is two things. There are like polynomials, non-parametric, polynomials and decreasing. We're adding a shape restriction, okay, and non-parametric and decreasing. So if you look at what are the widest of these bounds, it would be this one, which are the non-parametric. Non-parametric bounds without assumptions, okay, gives us a bound for the ATT that goes from negative 0.6 to 0.2. Then if you just start looking at the polynomials increase as you add more degrees of the polynomial. And then asymptotically, you can see that they will, asymptotically in the number of terms in the polynomial, they will converge to the non-parametric ones. Then you also see, like, let's consider 6 here just as an example, the value of introducing assumptions, right? Because, for example, here, you have the, whoa, that's not the one. Yeah, it's that one. Sorry. Here we have the polynomials without the assumption of the shape restriction and decreasing. And here we have the polynomial imposing that assumption. And you can see the same thing here and here. So you went from this interval to this interval by imposing shape restriction. And in particular, if you really care about, so for example, something like 0, then the first case will like be essentially including 0, be right there. Whereas in the other case, you just have a negative ATT. Okay, so the shape restrictions really matter in a lot of these cases. And even as you move along, there's quite a noticeably different, for example, in the upper bound, when you assume that things are decreasing or not. Of course, you have to believe that there are reasons to impose such an assumption. So polynomial bounds converge to the non-parametric bounds. I already said that. And shape restrictions can have a big impact. Look at k equal to 6. We did that already. Okay. The next picture that is interesting is extrapolating the late. This is a policy relevant treatment effect. Okay. So what's going on is this. Here, I'm going to write here. Oops. It's just the late from 2 to 3. Okay, this is this point. And so that's what you observe from the data. From the data, remember that there are 4 points of support of the propensity scores: P1, P2, P3, P4. But what we want here is just the local average treatment effect, where you just increase the propensity score of those that have P3, you just increase it a little bit. And here you have alpha. Okay, so you go from 0 and you keep going. And let me pull this back a little bit. Notice that here we have 48 and 78. Okay, so whoops, P3 is 0.48. When you add 0.3, you get 0.78, is P4, okay, which is another point in the support of our instrument. So then now you look at this picture, and what happens is this is the late from going from 2 to 3, and this is here the late on going from 2 to 4, which is identifying the data by comparing just P4 with P2, which is point identifying. However, anything in between these two is not point identifying. It's extrapolation. And so now, if you're just doing this model, use the restrictions that we learned, you see that here are the bounds on the late. And then you see, like, if just look non-parametric, they could be quite wide. If you just do non-parametric and decreasing, they're already a lot more narrower. And then if you just do a degree 9 polynomial and decreasing, you see that you have quite narrow bounds for this extrapolation. Okay? So this shows you, and again, is an example of a policy relevant treatment effect type of parameter where you just, increase the propensity score for these individuals. Of course, if you just keep increasing, at some point you hit a value that you observe as well, okay, which in this case is 0.78. So I thought it was a cool picture. All right, questions so far? All right, we're getting to the last part. We're going to talk about the application of bet nets. And the purpose here is to show how this approach is computationally tractable and how you can compute it using typically well-known software for linear programs. So the application is this bet nets. Okay, is motivated by the paper by Dupas, and this is an experiment when she randomly assigns price subsidies for purchasing bet nets. Okay, why? The outcome is whether the net is actually being used. How to promote cost-effective use of preventive health products. That's sort of like the question in the paper. Blah blah blah. I'm not gonna go over the details of the application, but you can imagine broadly what this is about. The data is just gonna be 1,200 households in Kenya, and the prices, what I called earlier, the subsidies are gonna vary from 0 to 200. What's the unit here? Doesn't matter. Like cash. So, and there's 17 different price offered, but only 4 or 5 were available to each village. Okay, and then everything will be conditioned on village and then average. So the first thing that we have here is the propensity score, which was estimated through Logit. Okay, and then, as I said, you have all the issues with villages and stuff, which I don't want to get into because honestly, as long as you are careful and read how they dealt with it, doesn't add much complexity to the application. What I care about is the next table, actually. So this is a table that we should pay attention to. Just don't look at all the numbers because they're overwhelming. I want you to look at the table in an organized manner so that we can all be on the same page. First one is that there are like 15 specifications here, okay? But if you just think about it, the reason why of this is that there are actually 3 groups, okay? There's this group, first 5, second group, third 5, and third group. And then as you can see here, you have, this would be what's our set S that we said before, includes an intercept, linear in the propensity score, least squares, and this 2 types of indicators of the instruments. Okay. So and then in each of these groups, you have 5 specifications that are just the degree of the polynomials that we're using, which go from 2, 6, 10, 20 non-parametric, 2, 6, and 20 non-parametric, and so on. So it's not so difficult. It's not there are like 15 that are like all completely different. Okay, you can just actually go like this, and that simplifies what we're looking at. All right, then you go to panel A, and then what you have here is lower and upper bounds for the average treatment effect. Okay, so and then what you see is that the bounds get larger as you go from more assumptions to fewer assumptions, meaning a more restrictive model to one that is more flexible, in the extreme being the non-parametric case. Okay, but the bounds go from 0.25 to 75, and this is the case where you essentially don't include a lot of S's. If you just go to the other extreme, the bounds go from 24 to 72. So see how, the adding assumptions doesn't necessarily affect both bounds equally. Here you have a lot of effect going from 25, okay, to 44 over here by adding more IB-like estimates, in particular these 3. And whereas the upper bound doesn't seem to, doesn't seem to be that much affected. Okay, 75 to 72. There's still an improvement, but that's what it is. Okay. Also note that when you impose a lot of assumptions, like, is a degree of polynomial 2, and then you add a lot of, say, IB-like estimates, you can just have an empty set. There's no solution to the model because you're imposing a lot of assumptions. You want to fit a lot of information that you have. Well, it doesn't fit. And so you have an empty set. It shouldn't be confused with like, oh, I have, great. It's just, I'm unidentified. I found nothing. So I'm just saying that misspecifications sometimes lead to things that are narrow. So, and that's a risk of like putting a lot of assumptions. But in this case, the extreme of that is that we get the empty set. All right. But notice how, just to continue that sort of argument, when you impose more assumptions, you have bounds that are more narrow than when you are try to be more flexible, right? Which is again stuff that we saw in the pictures earlier. As we add more assumptions, things get narrower. So it's great. And then I say, like, you just keep pushing, you're gonna have a model that is point identified. But if you just have something that it gives you point identification everywhere, in a case like this where you conceptually understand that you should not be point identified, then is worrisome. It's an indication that you may have too much structure. It happens often in IO. We're deviating here, but in IO, when we talk about moment inequalities later on, there are a lot of these models where people know that they're partially identified and they use moment inequalities, but then they just come and add all these assumptions on the profit functions and the behavior of the agents and whatever, and then just go and compute the identified set. It's like, oh, look, this is really small. I'm so happy with my identification. And at the end of the day, what happens is that the model is probably misspecified. So you combine partial identification with misspecification, you start getting weird results, in particular things that look really precise. So you have to always be careful about that. Anyway, coming back here, this is a common parameter of interest, the average treatment effect, but may not be so interest, okay? Because this is the policy relevant treatment effect of free provision, okay, with full take up versus no provision. So it's just saying, let's give the bet nets to everybody versus not giving the bet nets to anybody, okay? Perhaps that's not what you care about. That's why if we just look at the lower portion of this table, we get this alternative policy relevant treatment effect, which is free provision versus the market price, okay, which is the price at which people could buy these bet nets on the market. And so that is not identified as a late because you don't see that, but you can compute bounds using this approach. And then you can see here how, again, if we just go to the case where we have all these assumptions, and even if we're not parametric, or if we just want to be slightly more conservative and or less conservative and add a little bit more of structure and say, I'm going to just use the polynomial of degree 10, that the results are actually quite informative about a parameter like that. I mean, you're not point identify, but you still have a sense that this is roughly between 65 and 70%. Okay, so this is a significant effect. Of course, you can um, go to the other extreme here, and then you can say it's anything between zero point 0.5 and 1. But again, so it matters. You can see how in this case, and notice something that is also interesting. Whereas for the average treatment effect, we saw that adding assumption essentially had an impact on the lower bound. In this case, we see that we have a huge impact on the upper bound. So, of course, it depends on the geometry of all these sets that we're talking about, the script M and the B and so on. Now, the paper also used inference, okay, because as I said, they did develop an approach to do inference. And so it's certainly the case that inference, is not easy in these models. And so even in a case like this, right, where I said, look, what you obtain is actually quite informative. The minute that you add inference to that, it is informative, but it is still like, quite much wider than what you had before. And, this is again because it is difficult to do inference in linear programs in general. So you're going to see that oftentimes inference is the confidence intervals are going to be wide. Okay. So here's another example. And at this point, I don't remember why they don't report for the non-parametric case, probably because the theory didn't work. I don't remember that. I apologize, but I thought why that's the case. So I wrote here, statistical inference is a challenge for partial identification approaches, linear programs in general. Okay. And so it is, we know, because, we know how they were developed, that these confidence intervals are conservative. They could be excessively wide, but that's what we know so far. And so even though there's people working, this is still an area where, we may have much better methods in a couple of years, but that's where we are today. And so that's the end of today's lecture about extrapolation. Next class, we're going to talk about the outcome test. And now let's just move on to questions.